بسم الله الرحمن الرحيم. الحمد لله والصلاة والسلام على رسول الله. إن شاء الله اليوم نستكمل مع بعض في الفيزياء الإحصائية. الحقيقة احنا توقفنا عند هذا الاكسرسايز في هذا الفصل. calculate the dimension of BR is it normalized. احنا هنا بنحكي عن البي، هي عبارة عن رمز للاحتمالية أو probability، وطبعا احنا ميزنا بينه وبين البريشر أو الضغط. الآن احنا المفروض انه بي ار في دي في تمثل volume of the أو element of the volume، تمثل هنا ال probability، وهي المفروض تكون dimensionless، وبالتالي إذا تكون ال BR في ال DV dimensionless، عشان تصير dimensionless لازم تكون اللي هو DV. لو جينا نعمل الدايمنشن تبعها تكون عبارة عن دايمنشن. طبعا احنا بنعرف اساسا الدايمنشن تبع ال DV الحجم، طول في طول في طول او طول في عرض في ارتفاع، فبديني التكعيب. فبالتالي ال BR لازم تكون عكس الدايمنشن تبع اللي هو الحجم، وبالتالي بيصير كأنه الدايمنشن تبع ال BR هو الدايمنشن الحجم -1 أو الدايمنشن -3. طبعا بالتالي هنا احنا بنقدر أيضا نستفيد من هذا الكلام في المعادلة 2.18. خلينا نستحضر 2.18 هي موجودة هون. انه حنلاحظ انه البي ار دي في بتساوي 1 على ان ار دي في، انه نقدر نطلع الدايمنشن او الان ار على ان، وبالتالي او ان سمول المقصود فيها عنها. طبعا حنلاحظ انه هنا عندي لو عملت انتجريشن اللي هو ال NR أو NR small، المفروض yields the total number of molecules اللي بيظهر في المعادلة. قلنا 2.18 زي ما شفنا توي، أو في المقام تبع معادلة 2.18. طيب الحين احنا مفروض بدنا نسأل أنفسنا بعض سؤال مختلف، انه what is the probability لمين لوجود اي بارتيكل في بليس او في certain بليس معين. طبعا احتمالية وجود بارتيكل في مكان معين او في بوزيشن معين. ايضا ما هو what is the probability of the configuration of the system، توزيع او احتمالية توزيع البارتيكلز في سيستم معين. وطيب the probability of the particle will be in the volume لما يكون عندي volume dv1 dv2 إلى dvn. طبعا الحجم اللي بدي أخده حول بوينت معينة اللي هي عندي مثلا br1 br2. كل بوينت ممكن يكون إلى rn يكون لها حجم أو عنصر حجم معين. طبعا هذه كلها ممكن أسئلة نجاوب عليها خلال سواء هذا الفصل أو خلال دراستنا في الفيزياء الإحصائية. طبعا احنا هنا بما انه البوزيشن بقول لي of a different particles، ممكن ناخذ بوزيشن لعدة particles. لا يعتمد طبعا نقول في نحكي على الايديال جاز، هي ممكن ناخذ individual probabilities، بمعنى انه احنا ناخذ الاحتمالية الفردية لكل element حسب طبعا معادلة 2-10. احنا كانت بتدينا احتمالية عند البوزيشن R لمجموعة من البارتيكلز. يكون عندي بارتيكلز موجود في بوزيشن R، احتمالية وجود هذا البارتيكلز على بعد R حسب طبعا تعتمد على اليو ار وعلى الكي تي وعلى الاكسبوننشال وعلى ال NR0. الآن أيضا احتمالية لنفس هذا البارتيكل على بوزيشن R هي BR dV بتساوي 1 على N capital NR small dV حسب معادلة 2.18. طب لو أنا كان عندي مجموعة بارتيكلز بدي أقول BN capital للتوتال نمبر اوف molecules أو atoms أو البارتيكلز، R1 R2 R3 إلى RN. أيضا مضروبة في dv1 إلى dvn. هذا بده يساوي حسب المعادلة 2.18 المفروض br1 dv1 br2 dv2 br3 dv3 إلى brn dvn. بمعنى آخر ممكن أقول بتساوي summation إن r نوت أو 0 على n الكل اس ان اللي هو number of moles exponential minus 1 على كي تي. طلعت الكي تي برا السميشن اللي فيه المعادلة 2 10، طلعت الكي تي برا وظل اللي هو summation من اي بتساوي 1 إلى n البوتنشال لكل بارتكلز أو لكل مجموعة بارتكلز على بعد R1 R2 R3 اختصرت في RI مضروبة في الدي في 1 إلى دي في ان. إذا السميشن هذا للبوتنشال هو التوتال بوتنشال انرجي زي ما احنا شايفين الآن لمين للان بارتكلز للغاز اللي بيكون عندي أو للغاز اللي عندي. على أي حال في المحصلة أو إحنا بنعمل conclusion إنه probability density لقيت أنا بدي أحكي على حاجة اسمها probability density ل certain configuration لتوزيع معين لسيستم من البارتكلز تتناسب مع مين؟ مع الاكسبوننشال اللي هو أو ماينس الاكسبوننشال اللي هو للتوتال بوتنشال انرجي عندي. اذا هنا صار انه في علاقه ما بين البروبابيلتي دينستي الكثافه الحجميه او الاحتمالات كثافه الاحتماليه لوجود بارتكلز معينه في بوزيشنز معينه تعتمد بشكل اساسي على اللي هو التوتال بوتنشال انرجي. وطبعا هيك صار ممكن أنا أربط أعمل علاقة ما بين الاحتمالات أو الكثافة الاحتمالية وأيضا البوتنشال انرجي وأعتبرها بدلالة أو باليونتس إذا قست باليونت تبعت اللي هو الكي تي عندي هنا. عشان هيك هذا الرسم حنلاحظ إنها المحور السينات كأنه أنا بقيس الانرجي زي ما احنا شايفين الابسلون فاريانت باليونتس اوف كي تي، والمحور الصادات او واي اكسس عباره عن ان اي بالاربيتري يونتس. هنلاحظ التغير تبع هذه الكثافه الاحتماليه مع البوتنشال انرجي عند لو قست في بدلاله اللي هو اليونتس كي تي. هنا عندي في الحقيقة الفرع الثاني ماكسويل بولتزمان ديستريبيوشن موجود في البيج رقم 24. يعني هنا يمكن أنا بحاول ناخد فكرة أوضح عن الموضوع هذا. يمكن نحضر فيديو هنا لربما يكون
Maxwell-Boltzmann speed distribution. In this video, we deal with the Maxwell-Boltzmann distribution, which describes the distribution of the speeds of the molecules in an ideal gas. So let's get started. As already explained in the video on Brownian motion, the temperature of a gas is a measure of the kinetic energy of the particles. However, even at a constant temperature, not all the molecules in a gas have the same speed. After all, in a gas there are permanent collisions between the molecules. Some molecules are slowed down by the collision and others are accelerated. Thus, molecules with different velocities can be found in a gas. A gas usually contains a large number of molecules. For ideal gases, therefore, statistical predictions can be made about the frequency with which certain speeds occur. The so-called Maxwell-Boltzmann distribution describes such a speed distribution for the particles of an ideal gas. Such a statistical prediction about the speed distribution is only possible if a sufficient number of molecules are present. This is true in most thermodynamic cases. To get an idea of the large number of molecules in an ideal gas, imagine a football filled with air. The number of gas molecules in such a football would then correspond approximately to the number of 1-liter water bottles that would theoretically be necessary to completely fill the entire volume of the Earth with water. For such a large number of gas molecules, reliable statistical predictions can then be made about the speed distribution. We will discuss this in more detail in the following. Speed distribution. Using statistical methods, physicists James Clerk Maxwell and Ludwig Boltzmann were able to derive the shown formula for the molecular speed distribution in an ideal gas. For this reason, this function of the so-called relative frequency density is also called Maxwell-Boltzmann distribution function. In this formula, m denotes the mass of a single gas molecule. The constant Kb is the so-called Boltzmann constant. The temperature T must be given in this formula in the unit Kelvin. The given curve shows the speed distribution using the example of helium at a temperature of 273 Kelvin. Note that the speed distribution is independent of the gas pressure. In another video we deal with the experimental determination of the speed distribution in a gas in more detail. For ideal gases, however, this speed distribution can also be derived mathematically. We will also discuss this in more detail in another video. In this video, however, only the given speed distribution will be explained and discussed in more detail. Interpretation of the Maxwell-Boltzmann distribution function. The Maxwell-Boltzmann distribution describes the frequency with which certain molecular speeds occur in an ideal gas. In principle, however, it is not possible to assign a concrete number of molecules to a specific speed. One will never find a single molecule that has a certain speed exactly up to the last decimal place. One can only assign speed ranges to a concrete number of particles. This means the number of particles whose speeds lie within a certain interval, for example between 1300 and 1600 meters per second. Therefore, one chooses a graph in which the area under the curve between two speeds corresponds to the percentage of molecules whose speeds lie within the considered range. Thus, one does not speak of the frequency, but of the frequency density, frequency per unit speed interval. Since it is not an absolute frequency, which means not a concrete number of molecules, but a percentage, it is called relative frequency density. If, for example, there is an area of 0.2 in the range between 1300 and 1600 meters per second, this means that 20% of the molecules have a speed within this range. If one randomly selects 100 molecules in this gas, then 20 molecules would be among them whose speeds lie within this interval. The probability of catching a particle whose speed lies within this interval would thus be 20%. This example shows that the relative frequency density can also be interpreted as the probability density with which a randomly selected particle can be found in a certain speed range. With this interpretation, it also becomes clear that if only a certain speed is considered, the area under the curve becomes zero. Thus, the probability of finding a particle with exactly this velocity is also zero. This means that there is no particle with an exactly given speed. Influence of temperature on the speed distribution. The curve shown is an example of the speed distribution of helium at a temperature of 273 Kelvin. With increasing temperature, however, the maximum of the curve shifts to higher and higher speeds. The curves are stretched in length and squeezed in height. This results in a broader speed distribution with higher speed proportions. For all curves, however, it is true that the probability to find molecules with high speeds do not become zero even for very high speeds. This means that even at very low temperatures, there is a certain probability that molecules with very high velocities can be found in the gas. If this statement is applied to liquids, it also explains why liquids gradually change to the gaseous phase even far below the boiling point and thus evaporate. Even at very low temperatures, there are always some particles that have sufficiently high speeds and thus kinetic energies to escape the intermolecular bonding forces that are present in the liquid phase. They break away from the binding forces and thus escape from the liquid, so to speak. The liquid gradually becomes less until the molecules are completely in the gas phase. Since according to the speed distribution the number of particles that have such a sufficiently high velocity is relatively small, such an evaporation process takes a relatively long time compared to the vaporization process. However, as the liquid loses those molecules with high speeds during evaporation, the average kinetic energy of the remaining molecules in the liquid decreases. Since this average kinetic energy of the particles is in turn directly linked to the temperature, a reduced energy thus means a lower temperature, the liquid cools down. This phenomenon is used, for example, when sweating to cool the skin. Characteristic speeds, most probable speed. To characterize the speed distribution, different speeds are introduced, which are explained in more detail in the following. If a molecule is picked out by chance of an ideal gas, it is most likely that this molecule has a speed near the maximum of the speed distribution. At this point, it should be mentioned again that the speed distribution can be interpreted also as a probability function. The speed at the maximum of the distribution function is therefore also referred to as the most probable speed. Mathematically, this most likely speed can be determined by setting the first derivative of the Maxwell-Boltzmann distribution equal to 0. To solve this equation, we use the product rule. The term marked in red is to be considered as a constant, while the term marked in green and blue are our two functions. If we now apply the product rule, we get the following equation. We now solve this equation with respect to the speed. To do this, we first divide the equation by the constant term marked in red. In the equation obtained now, we can cancel out both the exponential term and the term 2v. In this way, we finally get the given formula for the calculation of the most probable speed. It turns out that the most probable speed depends not only on the temperature, but also on the mass of the gas molecules. The figure shows the influence of the mass on the distribution function, and thus on the most probable speed at constant temperature. For heavier gas molecules, the most probable speed will be lower than for lighter molecules despite the same temperature. For example, a molecular mass 4 times as large means only half as large a most probable speed. Characteristic speeds, arithmetic mean speed. Besides the most probable speed, the so-called arithmetic mean speed is also used to characterize a speed distribution. This is also referred to as average speed or just mean speed. The average speed is obtained by summing up the speeds of the particles, and then dividing the sum by the number of particles. Mathematically, this mean speed can be determined by integrating the distribution function within the limits from 0 to infinity, whereby the distribution function must be weighted by the speed. If we now use the distribution function, we can first multiply the speeds marked in red. After that, the term marked in red can be written before the integral, since it contains only constant quantities. The integral itself is actually not so easy to solve. However, a look into the mathematics formula collection shows the given term as the solution for this integral. With this solution, we can simplify equation 2 a little bit. To do this, we square both sides of this equation 2 to eliminate the square root. In this way, we get equation 3. We can further simplify this equation 3. Finally, we obtain the given formula for calculating the arithmetic mean speed. If one compares the formulas for the most probable and the average speed, one notices that the average speed is higher than the most probable speed. This also becomes clear when comparing the area to the right and left of the maximum of the distribution function. 42.8% of the molecules have a speed below the most probable speed, while 57.2% have a speed above the most probable speed. Thus, since more molecules have a speed above the most probable speed, the mean speed is shifted to higher values. To get an idea of the order of magnitude of the mean speed in gases, nitrogen molecules are considered, which make up the majority of the air with 78%. With a particle mass of 4.65 times 10 to the power of minus 26 kilograms, the nitrogen molecules have a mean speed of about 470 meters per second at 293 Kelvin. Note that the average speed of the nitrogen molecules in the air is thus greater than the speed of sound. In contrast to sound, a nitrogen molecule does not travel several meters, or even kilometers, in a certain direction. It will permanently collide with other air particles and constantly change direction. Such a distance without a collision is usually only a few nanometers, and is called the mean free path. We'll go into more detail about this in another video. Characteristic speeds, root mean square speed. In thermodynamics, one is usually not so much interested in the speeds of the molecules, but rather in the kinetic energies, since these are directly linked to the temperature, as we will see later. At this point, one might think that the mean kinetic energy of a gas molecule can be determined directly from the arithmetic mean speed. However, this is not true, because the kinetic energy is influenced by the square of the speeds. Thus, high speeds have a disproportionately large effect on kinetic energy. For example, a speed twice as high does not mean a kinetic energy twice as high, but 4 times as high. Thus, higher speeds influence the average kinetic energy of the molecules more strongly than lower speeds. Here is a simple example with 4 balls, each with a mass of 1 kilogram. The speeds are 10, 20, 40 and 50 meters per second. If we sum up these speeds and divide the value by the number of balls, we get a mean speed of 30 meters per second. If we use this speed for the calculation of the mean kinetic energy, we get a value of 450 joules. As already mentioned, however, this does not correspond to the actual mean kinetic energy. We can show this easily by determining the kinetic energy for each ball. For ball 1, with a speed of 20 meters per second and a mass of 1 kilogram, the kinetic energy is 200 joules. For the other balls, the kinetic energies are 800, 50 and 1250 joules. If we add up these energies and divide the value by the number of balls, we get a mean kinetic energy of 575 joules, and not 450 joules we calculated before. From this simple example we can see that to determine the mean kinetic energy we must not use the mean speed, but must average the kinetic energies. For this purpose, we must sum up the individual kinetic energies of the molecules, and then divide this value by the total number of molecules. If we set up the general formula for this, we can factor out the term 1/2 times m. We see now that for the kinetic energy the mean value of the speed squares is relevant. And this is obviously something different than the square of the mean value of the speeds. Therefore, the arithmetic mean speed must not be used to characterize the mean kinetic energy of the molecules. Rather, the arithmetic mean of the speed squares must be taken as a basis. In order to obtain the dimension of a speed, the square root of this mean value must be calculated. This speed is then referred to as the root mean square speed. To derive the formula for calculating the root mean square speed, the Maxwell-Boltzmann distribution function must be integrated from 0 to infinity, whereby this distribution function must be weighted with the square of the speed, and no longer only with the speed as was the case when deriving the arithmetic mean speed. Subsequently, the square root of this integral is to be calculated in order to obtain the dimension of a speed. We do not want to solve this integral in detail here, but only show the result with the given formula. We can now use this result in the formula for the calculation of the mean kinetic energy. First, we can eliminate the root and get equation 2. In this equation 2 we can cancel out the mass, and we finally get a very simple relationship between the mean kinetic energy of the molecules and the temperature of the gas. It turns out that the mean kinetic energy of the molecules depends only on the temperature. Thus, the temperature is a direct measure for the mean kinetic energy of the gas molecules of an ideal gas. This equation is remarkable because it links a macroscopically measurable quantity, in the form of temperature, to a microscopic quantity, in the form of the kinetic energy of a molecule. Relationship between the different speeds. The figure summarizes the different characteristic speeds. Basically, the mean speed of the particles is always greater than the most probable speed, and the root mean square speed is always greater than the mean speed. The different speeds are always in a constant ratio to each other, independent of the temperature or the mass. The average speed is therefore always higher by 12.8% than the most probable speed, while the root mean square speed is always 8.5% higher than the average speed. Maxwell-Boltzmann energy distribution. Since a certain kinetic energy can be assigned to each speed, the speed distribution can also be converted into an energy distribution. Instead of the distribution function for the speed, a distribution function for the kinetic energy is obtained. As already explained, the relative frequency with which a speed exists within the limits between v1 and v2 results from the integral of the distribution function. If the speeds v1 and v2 are converted into the respective kinetic energies e1 and e2, then a distribution function of the energy within these limits must lead to the same relative frequency. If both equations are equated, then the following relationship between the two distribution functions applies. The expression marked in equation 3 corresponds to the derivative of kinetic energy with respect to speed. This derivative corresponds to the product of mass and speed. In this way we get equation 4. Thus, equation 5 gives the relationship between the energy distribution and the speed distribution. If the speed distribution is now used in this equation 5, and the terms are rearranged in such a way that the term for the kinetic energy appears in it, then the given relationship is finally obtained. The terms marked in red correspond to the kinetic energy, so that the distribution function can be expressed solely by the kinetic energy. In this way we finally obtain the distribution function of the kinetic energy. The diagram shows the distribution of the kinetic energies for a temperature of 500 Kelvin. Note that this distribution is valid for any ideal gas at the given temperature, since the distribution function is determined by the temperature alone. The exponential term in the distribution function plays a special role in statistical physics, so-called Boltzmann statistics. This term describes in general the frequency or probability with which certain energies are present. The term called Boltzmann factor always occurs whenever random distributions of energetic states are involved. For example, also with the Planck's law of blackbody radiation. We will go into more detail about such a blackbody radiation in another video. We hope you enjoyed the video and found it helpful. Thanks for watching.
شكرا. يعني الحقيقة هذا الفيديو يمكن بيوضح لنا يعني كيفية اللي هو التعامل مع بولتزمان. فيه هو كمان يعني هنستكمل المحاضرة مع بعض، بس يمكن لساعة الفيديو الوقت بدي أتوقف لهان، وإن شاء الله خير.